hand it over. Hi, everyone. So we are the CARI Lab, and today we are super excited to share you guys with what we are doing. And specifically, CARI Lab stands for Computational, Autonomy, and Robotics Laboratory. And we have a bunch of robots. So you can see here, so there are the Husky robots, which is a wheeled platform, the mini cheetah robot, and the Go1 robot. These are like legged robots. And then there's a Fetch robot, which is a super old but very famous one. You can grab things. And before, so I talk about the details a bit about myself. So I'm currently a PhD student in the CARI Lab, and I'm mainly working on the SLAM robot mapping, robot localization. So I did my undergrad in Shanghai and did a master's here, and I developed an interest in robot perception. So about the lab, so our long-term goal is to enable autonomy. Specifically, we want the robot to navigate and traverse through unknown and unexplored extreme environment. We want it to collaborate in teams with other robots or humans, and we want to someday in the future attain to human level perception and autonomy. So here's an example of the autonomous navigation experiment we did a few years ago. You can see that. So specifically, this robot, which you can see on the left corner, the biped robot that's walking independently without any human intervene. There's a guy who is trying to walk behind the robot just for protection only. And the robot can identify where the road is, which is basically the white colored voxels in the map. And it will identify what is the best path for it to navigate along the white road. We use technologies like neural networks, deep learning, and planning and biped control to make the robot walk successfully. You can see that in the end, when you walk to the end of the wayfield, we built a very high quality map using sensors like camera and LiDAR. And besides the autonomous navigation on biped robot, we are also doing some other cool stuff. For example, Chris, do we have a voice for this? In this project, so we are trying to make a Fetch robot interact with the visitors of the University Museum, Michigan Museum. So it will navigate by itself, trying to identify different paths in the museum and discuss, talk, and interact with the visitor. So besides this research project, we are also working with the students' teams in the, for example, undergrad and master students. For example, this is a competition, Robotics competition, where the student teams and some students in our lab are working together, trying to make the robot like navigating by itself. And although it is a simulator, you need still some techniques like navigation and object detection. So this is basically about like a brief overview of what we are doing application-wise. So in the next step, we're going to talk about some technical details.
Hey, so my name is Joey Wilson. Yeah, so I did my undergrad in California, and then I was originally going to move to Singapore, but then the pandemic happened. So I ended up here where it's really cold. been through 2 winters, so yeah, I'll get through this one. Yeah, I started out in electrical engineering and then like bounced around. So then I did some software, computer engineering, but I wasn't really too interested in like making websites or apps. Yeah, but then I ended up with robotics because it's a cool area where you can apply so many different domain areas, a lot of different knowledge in different areas. Yeah, so right now I specialize in perception, and I'm currently taking classes in neuroscience, which I think is very fun because it's cool to think about how we think as well and apply that to robots. So earlier we saw the CASI autonomous navigation, and a large part of this is how to interpret the world. So taking labels such as, what is a chair, what is a desk, what's a person, and how to put that in your world model so your robot can understand the environments. And what we also care about is understanding what the robot is observing, not just having the robot observe it, but having this shared human robot understanding of the world. And when we're watching this video, we can see there's a sidewalk, and we can see that the robot is clearly distinguishing where the sidewalk is. So that's a lot of what I've been focusing so far on in my PhD. And it gets more complicated too, because in this environment, the terrain is pretty even. There are no moving objects, but as soon as we start incorporating those things, it starts getting really complicated. So like one of the papers that I worked on is how to make this algorithm you saw in the previous one more robust. So deep neural networks, they can be kind of finicky because you don't necessarily understand exactly what's going on within it. But we made this mapping framework where you can tell exactly what the network is learning, because it's learning things like a pole is a tall object, and a road is like this flat object. And based on what those semantic labels are, you can learn to incorporate that within a world model and make it potentially more robust. And then the other part that I focused on is also how to make these algorithms work in dynamic environments, because the real world is very complicated and things are always moving, which can be a huge challenge for your robot. So this is like a data set that we created, and we also made an algorithm for it. And like I mentioned earlier, this shared human robot scene understanding is very important, because when we're watching this, we know exactly what the robot is seeing. We can see the cars, the buildings, we can see the people and the crosswalks, and we can have a sense of trust with a robot, because if we're ever going to get in a self-driving car one day, we should probably be able to actually trust it. Okay, so next is localization and state estimation.
Hello, my name is Justin. I did my undergrad in Taiwan in mechanical engineering. And after that, I came here to do master in robotics. And I started to do research with Mani and then become a PhD student in his lab. My main focus in my PhD research is localization and state estimation. So those are some jargons. What those means is that the robot is trying to know its own location and orientation, or like heading in the world. So that's what I'm trying to do. So the first project I worked on is continuous visual odometry. So visual odometry means that we use just camera to estimate the position of the robot or a car in the scene. So you can see this is actually like a car driving on the road, and we use camera information to estimate where the car is in the road. And after this project, I worked on the Minishita robot. So we built a perception sensor suite on top of the robot. So basically, the robot came as a blind robot. It doesn't have any camera on top of it. It cannot see the world. So we built like a sensor suite with camera on top of it, so that basically enable it to see the surrounding environment. So with this, we can do the visual odometry or SLAM to estimate the robot's position, and then we can build a map of the world surrounding it. Another project I worked on is using a neural network to estimate the foot contact event of mini cheetah. As you can see in this video, when the foot is contacting the ground, we can use this additional information to correct the state estimated from some algorithm. So we train a neural network to estimate the foot contact event. So we know which leg is in contact with the ground, and then use that as additional information to correct the state. And then we can estimate and reconstruct the trajectory of the robot when the robot is walking. And in this work, I did not use any camera sensors. You can see that the robot actually walks in a variety of different terrains. Contact estimation can be accurate and used to estimate the correct trajectory of the robot.
Or the satellite map. Oh, that's the best part.
So yeah, this is the estimated trajectory, and if we overlap it with the satellite map, you can see that the reconstructed trajectory is very close to where the robot actually walked. This video is on YouTube. You can go check out.
And my name is Cynthia. And I did my undergrad in Taiwan doing mechanical engineering. And at that time, I was mainly doing designing and manufacturing for medical devices. Then I want to switch the area. I want to learn more about computer vision stuff. And I applied for grad school here in Michigan. I was doing master's degree in robotics and doing different research projects in different labs, and end up in Mani's lab doing a PhD. So I remember when I was in undergrad, deep learning was just started to blow up, and then people are skeptical about it. And at that time I was saying, I won't do research in deep learning because it's just a black box. We don't know anything about it. But now, after learning more about it, I know it's more about math and optimization when you learn all the things in this huge structure. So our lab also do some research in the deep learning algorithms. First one is we are registering the point clouds. So point clouds are these small spots that represent some 3D coordinates, like the XYZ values of the points. So some sensors can give you those 3D point clouds. And then for point cloud registration, we are finding the transformation between the 2 point clouds. So we know if it is rotated or translated, and we can find how much it moved. Traditionally, we will need to find the correspondence between each point, like which point is correspond to which point. But then using deep learning, we can learn we saw called equivariant features. That is when the point cloud is rotated, the feature is also rotated, and we can use this property to further find the transformation between the point clouds. And then we also have more efficient deep learning networks to learn the SD3 equivariant features. So previously, it was only about rotation, but for SD3, it includes rotation and translation. So it is a more complete network that can do more things. Another visualization is that you can see the left side, the point cloud is rotated, and then later it will translate. And then you can see our representation of the point cloud can remain the same if we use the transformation invariant features we learned from the network. And other methods will change when the point cloud moves. So this can be used in place recognition. That is for a robot to know where if it has been visited this place before. So you can see it is traveling around the road, and then it can highlight where it has previously visited with the reddish color. And it can also be applied to point cloud registration, which is finding the transformation between point clouds, as I previously mentioned. Another area, research area we did in our lab is using neural network to predict the depth from images. So if you know, there are sensors that can give you color images and then the depth images. And also you can obtain some 3D information from like LiDAR sensors or other 3D sensors. But sometimes if you are limited with a resource, you can only using one single monocular camera. How could you predict the depth information from that one single color image? Would be critical, and getting the depth information is beneficial for the algorithms we're doing. So as you can see, this is a network that predict the depth information, and compared to the baseline is better and it's more smooth than just using the LiDAR sensors.
Yeah, so just now we talked mainly about the perception. So we go through how the semantic mapping works, how the robot localizes itself, and how we use deep learning to help to learn some special features for the perception task. But now we want to do something that's besides perception. For example, here in our lab, some of the students are working on the multi-agent systems. So imagine that like in like 2 years ago when COVID was hitting hard. So we have like some resources, and we want to use the robot to deliver these resources to different destinations.
Requirements are jointly optimized.
Okay.
You could see the agents meet at the same location to conduct a task, avoiding the red high-cost regions in their route.
Go quiet.
Yeah, so I think it's better for me to explain this. And when you have this, like when you have limited resources and limited number of robots, and you want to deliver things around, and this becomes optimization problem. So you want to estimate what's the best way to deliver to distribute these robots to different places back and forth, so that you can use the least number of energy and use the minimum amount of time. And if we push this problem a little bit further, so what if the targets are not defined? So in the previous example, we clearly know where the targets are and what is the amount of like goods we want to deliver. But in this example, we want to the constraint, we want all the tasks to be learned by the neural network. And you can see that even the map itself is a more complicated terrain situation. You can see the example. There are 5 different task types, more task types, and 6 agents. And we want the robots to learn by themselves where it should go, and they should work together, communicate with each other. So besides the multi-agent system, so our lab is also doing some control work.
Hello everyone, I'm Sang Lee, a third-year PhD student in the Minus group. I did my undergrad in China and spent 1 year in California as exchange student. My first research is about state estimation for batteries, as like electrochemical systems. And then during my exchange studies, I switched to a robotic system, and in California, my research topic is state estimation about liquid robot. And currently, my research is about the control on for liquid robot, and probably a little bit on the theoretical side. For liquid robot, it is very complicated. For example, for the mini cheetah robots, we have 12 joints, and 12 joints, so it looks very hard to control. But when we launch the experiments, we do not really using such a complicated models, but we assume the torso is a rigid body. It's just like a cup or a rock base. So we only need to plan the ground reaction force. That's the force acted on the ground, so we can control the motions of the torso of the robot. As for the motion of the torsos, it can be modeled by Lie group systems. That is evolving on a surface of the nonlinear surface. The conventional method assumes that you can do some linearizations to make it a linear system in vector space, but it will give a very complicated linearization schemes. But in this research, we linearize it using the specific structure of the Lie groups, so we can make it a state independent linearization, so that can greatly reduce the complexity of the algorithms. Also, based on this linearization schemes, we can also have a more simpler cost function designs. That is on the right hand side, we have a quadratic form cost function that is very easy to solve. We can use any Newton method or something to obtain the minimum points. But for the conventional method, we have a very complicated shape of the cost function that is very hard to optimize. So that is about my research. Thanks.
Yeah, so that's basically a very brief, super concise introduction of the landscape of our research. And we are super happy to discuss about more details if you guys can reach out to us. And we are the CARI Lab, and this is our lab website. So I guess that's it for our presentation. So do you guys have any questions?
We can talk about anything, doesn't have to be related to the research. Yeah, it could be like grad school experience or something. Yeah. How we like working in Monty's lab.
So if you when you were showing the voxel map, how many voxels do you have to collect and store if you walk I don't know, 100 meters or a kilometer?
Oh, absolutely. This is a very good question. So in the so Joy and I can introduce our experience because we are doing different experiments. So the experience might be slightly different. So in the electro robotic experiments, I think in every second we are producing more than 10,000 voxels at the same time, and this accumulated, which means that so the longer the robot walks, the more voxels we are handling. If you can count, there's maybe mediums. It's huge.
Yeah. So, it of course depends a lot on the resolution, which also depends on what application you're doing. Because if you're in a room, maybe you need 1 inch accuracy. But if you're driving, it probably doesn't matter as much since it's a large structured environment. But yeah, even if you're going with 10 centimeter, 20 centimeter voxel resolution, it grows extremely quickly into the millions if you're doing a global map. And as you can imagine, that can be very, very, very slow to query. So one of the projects that I'm working on now is taking this framework where we have, so in like the last paper, what I did is worked on expanding what we had and making it run in real time. We can run like 100 hertz for a local, dense local update of the voxels using the Bayesian kernel inference framework. But the problem, the bottleneck is still that you have to query whatever is the local region. Because like I said, if you're doing a global map, there could be millions and millions of voxels. Finding whatever is local can be pretty challenging. Yeah, so actually like what I'm working on now is adjusting that to be a local, dense local map. In that case, now we're looking at maybe a few 100,000 voxels. And actually, by using like the power of GPUs, you can perform that update extremely quickly. All right, any more questions?
What's the relationship of what you do with this building? Marine robotics and.
How about Monty, do you want to answer that question? This is your lab.
Yeah, I can tell you that. No, working on ships and boats and dealing with water, I promise you, is very intimidating for these guys. So, the reason they don't do it because they don't know how to do it. But I am trying to build more projects towards that. At Robotics was one attempt to that. First of all, doing underwater robotics and just dealing with water is very time consuming and hard to do experiments. So a lot of these robots that you see is in the lab. It's very easy to get results and publish paper. You just go outside of the lab and just run the robot, collect some results. The reason we do it because the math and algorithms are often transferable to different domains. So it is possible to solve similar problems in other domains. For example, the control and Lego robot, you can do it on boats and ships as well. But it's harder to do experiments. So hopefully we will do more, and that's where you guys come in. So you might think that you don't want to interact with you, but we do. If somebody shows up and says, I want to work on controlling boats and ships and surface vehicles and underwater, that's great because you bring in the knowledge from that domain that I don't even have much of that. In return, we can teach you algorithms and how to code robot, for example. And then a mix of that will be something that is often in the marine domain, marine robotics. So that's how we can be friends.
Yeah.
But in the future, hopefully, we see more of it. Now, one thing that I talked with Armin, for example, Professor Torgen, I said it will be very cool to make a big ship autonomous. He said that you probably don't want to work on that because if you make a mistake, you're going to kill a lot of people. Whereas if anything goes wrong with these robots, I mean, at worst, they can get injured. I'm not going to be responsible. So there are some barriers, but I think, for example, the ocean cleanup company, I don't know if you know that. I love that company. They go around with ships and collect all the trash in the ocean. They wanted to make those ships autonomous initially. Then they realized it's really difficult. So I think that's going to be the future. That's a very cool project to make a fleet of ships autonomous, and then they can do some tasks like cleaning up, or it could be just monitoring and surveillance. I think there are a lot of opportunities in the marine domain. The knowledge is similar, but it needs domain experts and probably new projects.
Yeah, I agree with what Monty said, because that's definitely like one of the reasons I'm interested in like computer vision or perception, is because it's applicable to so many different applications. And like from my perspective, like all the research that I do, I have to demonstrate on wherever the funding is coming from. So for me, that's off-road vehicles. So anything I do, I have to demo it on something driving. Yeah. And I'm sure everybody else can probably attest to that.
Hey Manny, what's the status of our Robotics team right now? We just don't have enough students.
The Robotics, I don't know if you know, Dave Singer with James
Collar.
they built the ship. I was, I think before COVID, or maybe
Yeah.
around that time. Then he thought this is too much, I'm out. So, but there is a ship there's a boat somewhere, they built it. Then it was around COVID time, then I thought maybe I take over and do some work on the software side. So there's a really good simulator. We did a lot of work on building the software, object detection, planning, and navigation, making the robot to move from, one point, navigating between buoys and all of these things. Then gradually, people left, just graduated, and you don't have anybody working on it. So right now, nothing going on. But everything we did, we have some software and in the simulator, it works. And there's a physical robot. Just need a group of self-motivated people to just show up, say, we want to do this, we want to go to the competition. And it's not going to come from other buildings, but obviously it should come from this building. That's the problem now.
Yeah, we have the boat in storage, so if anyone's interested.
Yeah, it's a lot of work, but the simulation part is easy. If you like to get your hands on software and learn some autonomy solutions in the marine domain, this is a good setup. You can reach out. You don't have to work on it. If you just want to have access to it for yourself, that's also fine. Hopefully one day again. I'm getting a postdoc from Korea. His background is, Lisa's helping with that, hiring him. His background is marine robotics. So my goal is to build, the boat is still difficult. My goal is to build small robots that even you can, in your bathtub, you can just drop it and you can play with it. Before bedtime. You control the robot. So if it's small and cheap, then we can just build many of that, and then it's easy to break it and test algorithms on it. So maybe that's a better way. But also we can send it to high schools and then just teach people from earlier days. So hopefully he will be a momentum to do more work on the.
Yeah. And then I'm not sure what position everybody's at in their academic career, whether undergrad or graduate. But I started in the master's program and met Mani, and now I'm doing a PhD with him. And a lot of the students that I've worked with in Mani's lab are now doing PhDs at Michigan or other great places. So yeah, if any of you are interested in pursuing academic career or working on cool projects, yeah, working with Mani is a great place to start.
Usually.
Yeah, so because speaking from my personal experience, I did a lot of software side internship in my undergrad, and then starting from grad schools, I start to stay more time in the lab. And my personal feeling is that in the lab we have more more self-motivated, and we can, as a student myself, I can have more control over this project itself. While in my industry internships, I found that I'm more following what my boss told me to do. So I like this kind of freedom, academic freedom, and also this prepared me very well for later my PhD career. So more questions? Go ahead.
Are you guys by any chance familiar with the sail drone concept?
So could you explain a bit more about the sail drone concept?
Yeah, well, so it's being used increasingly with for oceanography or for it. I think the Navy is exploring it a little bit, but basically the idea is it's an autonomous surface vehicle. It's sailing, so it's not powered. But it is producing electricity either through a turbine or, depending on where it is in the world, either through a turbine basically up north where there isn't much solar, or farther south or near the equator, they're able to use solar power, obviously, or just as they get away, basically away from Alaska. But the idea is at the moment, they're operating autonomously. They've sent them into hurricanes, and I'm wondering, in terms of that sort of concept, is that something that just sort of the idea of an autonomous surface vehicle for oceanography or observation or anything along those lines, something that you guys have looked at all, and particular challenges you think that would be encountered and sort of like why was this, any insight into why this company was able to make some progress into making that autonomous?
Yeah, I think this is a very cool concept. I haven't actually heard of this company before, but I think their way that they distribute a lot of ships and let it sell by themselves, I think this is a very cool concept. But one challenge I can guess is that, so I was wondering what kind of sensors they are using actually, because they're operating on the ocean, they're operating on such a large scale in such a large environment. How do they locate themselves, and how do they actually understand whether they can go to a specific position without any collision, and how do they if they I assume that there are lots of sailing boats like this, and how do they share the information, share the 3D environment with each other? So do you guys have anything to comment on this?
Not directly on that part, but one problem that I think would be like fun to work on is because it's reliant upon light. So learning how to actually operate since you have limited energy, and then also how to move in order to maximize how much light you are obtaining. Because that sounds like a fun Bayesian inference problem. Yeah.
Your lighter, by the way, doesn't work here if you're underwater. There's nothing to see. And if you have waves, that's a very difficult control problem. I think you guys probably maybe you learned this in terms of research, how to calculate that load on the ship, and then when you want to design it, I think that's an important problem. It will be very important for controlling the robot as well. If it's battery powered, then you can get 30 minutes more. But I'm not familiar with that robot. It's called
Sail drone.
Sail drone.
Yeah. There are two variations. There's a smaller one that's been there for a few years, I think, and they just built a larger scale version. But it's being used for like oceanography, or I think the Navy's exploring it for surveillance stuff.
The one thing I'm hoping to find is that some builders, some people here who like to build marine robots. The problem is most people like to work on algorithms because you only need a laptop and internet. It's easy to find jobs. We don't have enough builders. Less people like to build things and make it move. So if you guys are builders, that's also a great way to break the ice. Talk to me, and then build something like that. You need people who know design and also know the knowledge of the marine environment. And I think that's what your training gives you. They don't know how to design any robots. I have to buy all the robots.
Yeah, building robots is super difficult. So I remember the original video, the video we showed in the first one, the biped robot, we spent like at least $10,000 or $20,000 just to design a suite holding all the sensors. And in the second one, the Minishita one, so Justin has more experience in this. We also spend many times, a lot of iterations just to iterate over the design of the sensor suite. This is like the kind of builder experience that a lot of us lack, and we are very desperately looking for people who are experienced in this field and work with us.
Anybody else? All right, thank you so much.